Hello, welcome to the course Excelling with Mathematical Modeling. Today we will be talking about an interesting model, smoking model. So when somebody inhales a cigarette, so as you can see in the video, lots of toxic gases that get inside. One of them, which we call nicotine, so that affects the brain. So what does this nicotine does is, we will see that it highlights a part of the brain which actually give you a very pleasurable feeling. So as those parts gets highlighted, that means you get addicted to the smoking. So as we all know that the smoking affects the lungs due to lot of toxic gases, lot of toxic things or amounts that get inside the body, and one of them is called cadmium. So this cadmium, they gets inside the lungs and they damage these lungs. So we will be talking about this smoking model where we model this amount of cadmium in the body. So some information is that each year a person smokes a single pack of cigarettes a day will absorb about 2.7 milligram of cadmium, which is an extremely dangerous heavy metal pollutant, and it's very toxic as you inhale the cigarette. So for simplicity in the model, we assume that this cadmium, it is absorbed at the end of the year, and the elimination of cadmium is at the rate of 8%. That some people eliminate this cadmium from their bodies each year at the rate of 8%. It could be 6%, 7%, even 9%. It depends from person to person. So with this information, mostly the elimination of cadmium at the rate of 8% and 2.7 mg of cadmium every year is added. Let's model this smoking problem. So if we take Cn, that is the amount of cadmium in the body at the end of n years, and R is the removal rate of cadmium, and A is the yearly absorption of cadmium. So if we now model this, it is going to be Cn, which is Cn minus 1. The removal rate is R, so R times Cn minus 1, and the absorption rate is A. So this is the amount at the end of year n, this is the amount at the end of year n minus 1, and removal is R and addition is A. So if you want to now find the equilibrium point, so all you have to do is replace Cn and Cn minus 1 by some C star, and if I substitute it here, I will get C star equal to C star minus R times C star plus A. This and this cancels, and I get C star is equal to A by R. So this is the point of equilibrium. If you want to see the stability about the equilibrium point, C star equal to A by R. So let me rewrite the model. Cn equal to Cn minus 1 plus r times Cn minus 1 plus a. So, we put Fc is equal to this function C minus Rc plus a, and your f dash c is going to be 1 minus r. So, condition for stability is f dash c, which is equal to mod 1 minus r, must be less than 1, and you will have the system is stable about C star equal to A by R. Now, before we check this numerically, let us derive a generalized formula for this Cn. So, we have Cn is equal to Cn minus 1 minus Rcn minus 1 plus A. Let us assume that initially there is no cadmium inside the body. So, your C0 is equal to 0. So, I can have C1 by putting n equal to 1. This is C0 minus R times C0 plus A. And since your C0 is 0, I only have A. Similarly, I put n equal to 2, I get C2, which is C1 minus R C1 plus A. So, I have C1 is A. So, 1 minus R into A plus A, and this can be written as 1 plus 1 minus R multiplied by A. Similarly, C3 by putting n equal to 3, this is C2 minus R times C2 plus A. So, 1 minus R times C2 plus A, 1 minus R times C2 is 1 plus 1 minus R multiplied by A plus A. So, I take this A common from this and I multiply this, I get 1 minus R plus 1 minus R square plus 1 multiplied by A. So, I can get C3 equal to 1 plus 1 minus R plus 1 minus R whole square whole multiplied by A. Now, if you look at the result, I have C1 equal to A, C2 equal to 1 plus 1 minus R into A, C3 as 1 plus 1 minus R into 1 minus R whole square into A. Similarly, I can write C4 is equal to 1 plus 1 minus R plus 1 minus R square plus 1 minus R cube whole multiplied by A, and as we proceed I can write Cn is equal to 1 plus 1 minus R plus 1 minus R square plus 1 minus R cube. So, here it is 1 less 1 minus R to the power n minus 1 whole multiplied by A. This is GP series, and we know the formula, that is 1 minus the common ratio to the power n by 1 minus 1 minus R multiplied by A. So, I get Cn is equal to A times 1 minus 1 minus R whole to the power n divided by R. So, if I know the value of R and I want to find what is the amount of cadmium at certain time, I can just substitute where your A value is given, that is 2.7, and R is 8%, which is 0.08. Now, let us check this solution numerically. So, we will be using Microsoft Excel. I already have it open. So, the value of R and the value of A. the value of R is 0.08 and the value of A is 2.7. So I just okay. So this is the n, this is the number of years, this is equal to 0 plus 1, and let me drag to few values, say 50 of them. Okay. Now the formula is, or the model is Cn that is equal to Cn minus 1 minus R times Cn minus 1 plus A. So Cn, the amount of cadmium at year n, this is the amount of cadmium in year n minus 1, and there is a reduction of 8%, so R is 0.08 of the amount in year n minus 1 plus a constant input of 2.7 every year. And initial value is taken to be 0, we assume there is no cadmium, and then this is equal to Cn minus 1, which is this, minus R times, which is a constant, multiplied by Cn minus 1, which is this, plus the constant value of E, which is 2.7, and I make this a constant by putting dollars and enter. So if I drag the values, let's see how much. Okay. So I highlight this, go to insert, click this value and this one. So I can write this as smoking model. I want to enter the axis title. So this is year, and this is the amount of cadmium. So this reaches some steady state value, which I can see as 33 point something, a little more, yeah. So if I drag these two, a little more value, yeah, so it reaching some 33.74 or 33.7, yeah, 75. Yeah, so 33.75. So 33.75 is the equilibrium value, and since this model is stable, because you remember you get mod of 1 minus R, and R is positive quantity 0.08. So 1 minus 0.08 will, the modulus of that value will be less than 1, and hence this model is stable with these parameter values, and you get the graph like this. So as you have noticed that the condition for stability is mod R minus 1 minus R, and if you check with this particular value, you can see that mod 1 minus r is going to be 1 minus 0.08 modulus of that, so 0.92, and which is less than 1. And hence your system is stable about the equilibrium point A star by r. And if you substitute this value 2.7 by 0.08, you will see that this is something close to 33.75. And in the graph you have seen that this particular value starts from 0 and reaches the value 33.75. Now if you want, okay, what will be the amount of cadmium after say 20 years? So all you have to do is that you have to write the formula Cn is A by R 1 minus 1 minus to the power n, where your A is 2.7, your R is 0.08 and your n is 20. So you want to calculate what is the amount of cadmium after 20 years. So you just plug in these values and you get 1 minus 0.92 to the power 20. And if you simplify, you will be approximately getting 27.37 mg of cadmium. We next move to another interesting model for the smoking case. Suppose we have Pn. We tell them as non-smokers, but they are potential smokers, and Sn to be the smokers and Qn to be the smokers who has quit smoking. So this model is about smokers, the non-smokers and the person who used to be smokers but then they quit smoking. So if you want to model such thing, so this is the number say after n years. So Pn plus 1 will be equal to Pn, Qn plus 1, sorry, Sn plus 1 is equal to Sn and Qn plus 1 equal to Qn. So we first write this one, and then there will be an interaction between the non-smokers and the smokers, but these non-smokers are potential smokers and somehow they get attracted to the smoking, say passive smoking, where they can actually inhale the smoke and they get attracted to it and start smoking. So from this non-smoker group, they will move to the smoker group, and this is the quitter at a rate beta. So this is Pn into Sn. Now this is the one who come across with the smokers, the non-smokers one get addicted or get interested or attracted to the smoking and move to the smoker group. Now from the smoker group, due to whatever may be the reason, the health reason, or somehow they don't want to continue smoking because they want to be healthy, so a part of them now goes to the quitter group, that is they who were smokers but then quit smoking, and that happens say at the rate alpha, and here some alpha times Pn Sn. Now of these category of person, there will be always a natural death. So you put a natural death mu times Pn, mu times Sn and mu times Qn. So, this gives you a model among the non-smokers, the smokers and the person who has quitted smoking. We call them quitters. So, one more time. So, this is the non-smokers who comes across with the person who is smoking, and then from this non-smoking class they go to the smoking class, and from the smoking class there will be always some person who want to quit smoking, which is happening at a rate alpha, and then come to the quitter class, and then these are the natural death of the persons. So, minus mu times Pn minus mu times Fn minus mu times Qn. Now, I leave this model to you. I give you some numerical values, say beta is equal to 0.2, then your mu is equal to 0.04 and your alpha is equal to 0.12. You take the initial conditions and use these parameter values to get different dynamics of this model, and use Microsoft Excel. We have done so much examples, I am sure you will be able to solve this particular smoking problem. So, with this we come to an end of this interesting session where we have discussed this smoking model. In my next lecture we will be talking about this price and demand model. Till then, bye bye.